Hello and welcome to this fluid mechanics lecture related to thrust on partially or fully immersed surfaces. Here's an overview of the presentation. We commence with some background information related to various presentations that would be useful to review and some underpinning knowledge related to the study of fluid mechanics. Next we have an introduction to thrust on fully or partially immersed surfaces. We have example 1. Where we're calculating the thrust from water on a retaining wall, for example as in a swimming pool. We have exercise 1A, where we're calculating the thrust from oil on a fuel tank wall, and exercise 2A, where we're calculating the thrust on a dam wall for two different scenarios. And here are the approximate start times related to the various sections shown on this slide, should you want to directly review a particular section, but please note time stated are rounded to the nearest minute. Overview of presentation continued. Next we consider moments generated by thrust on immersed surfaces. In example 2, we find the force in a sluice gate retaining cable. This is a typical scenario we'll be considering, having our sluice gate and finding the force in the cable attached to the top of the sluice gate. We'll outline this scenario in greater detail later in the presentation. Just note here for reference is a description of a sluice gate. Then we have exercise 1B, it's based on example 2, we're finding the force in a sluice gate retaining cable, and exercise 2B, again finding the force in a sluice gate retaining cable. Slightly different scenarios between exercise 1A and exercise 2B. Then we have question 1B and 2B, again finding the force in a sluice gate retaining cable, but there are no solutions provided for the questions. Then we have exercise 3B, a scenario with fluid on both sides of the sluice gate. So unlike all previous questions that had, for example, water on one side of a sluice gate, the scenario in exercise 3B relates to a separator plate, shown here, that has fluid on both sides of the plate. So we have a force generated from the fluid on the left hand side of the plate and a force generated by the fluid on the right hand side of the plate. And both are offset from the base of the plate, so they generate a resultant moment about the plate. This is a different scenario from the previous sluice gate problems. I will leave with exercise 4B to attempt at your own pace, which is based on the solution of exercise 3B. Here are the approximate start times related to the sections shown on this slide, should again you want to review a specific section. Note that all times are rounded to the nearest minute. Let's briefly consider some background information related to the presentation. For your reference, there are two previous presentations that contain underpinning knowledge associated with this presentation. The first one is Hydrostatics Introduction, outlining various definitions, terminology, calculating pressure within a fluid, and also introducing mass density, relative density, and weight density, and also various conversions between the various densities and various units of pressure. The second hydrostatics presentation relates to calculating pressure due to self-weight of the fluid, in which we define the formula pressure P is equal to rho GH. Here's some specific background underpinning knowledge related to this presentation. You need to be aware of the term gauge pressure, which is measured above atmospheric pressure. So 1 bar absolute pressure is equal to 0 bar gauge pressure. Absolute pressure is measured from a perfect vacuum. We need to be able to calculate pressure due to self-weight of a fluid. That's the formula pressure is equal to rho GH. We need to understand the characteristics of a fluid, such as pressure always acts normal to a surface. We need to be aware of the different types of density, such as mass density, Greek symbol lowercase rho, and relative density, Greek symbol lowercase sigma. It's very useful to be aware of the density of fresh water. The mass density is 1,000 kilograms per meter cubed, or like we've written is 1 ton per meter cubed, or having a relative density of 1. We need to understand relative density conversions. For example, a substance with a relative density of 7.84 has a mass density of 7,840 kilograms per meter cubed. In other words, we multiply by 1,000 here. We need to be aware of density conversions, for example, from ton per meter cubed or megagram per meter cubed to kilograms per meter cubed, multiplied by 1,000 for the conversion. And towards the end of the presentation, we'll need to be aware of the principle of moments. We need to be aware that the summation of the clockwise moments equals the summation of the anti-clockwise moments for equilibrium, something we've extensively covered in our beams and bending presentations. Very briefly, here are a few extracts from the previous presentations. Extract here tries to show that pressure always acts normal or right angles to a surface. Extract here from a previous presentation just shows various conversions between different units for density. For example, 7,840 kilograms per meter cubed is the same as 7.84 tons per meter cubed, the same as 7.84 grams per centimeter cubed, and the same as 7.84 megagrams per meter cubed. It shows the use of unity brackets here. There's a separate presentation related to unity brackets. Here's an extract from the previous presentation related to the proof of the formula pressure is equal to rho GH. And finally, an extract from the previous presentation comparing absolute pressure, absolute zero pressure here, with zero gauge pressure here. And there's a 1 bar difference between the two. Again, all this work has been covered in the previous presentations. Brief definition of thrust. In fluid mechanics, thrust refers to a force exerted by a fluid, that can be a liquid or a gas, on a surface. And this thrust acts perpendicular, normal, to the surface. Note that thrust is a vector quantity, so has both a magnitude and direction. The usual symbol for thrust is capital F. And as thrust is a vector, it can be represented by an arrow. So when you start on the right hand side here where we have a fluid contained behind a retaining wall, then you can see that we have a force generated by the fluid shown by the symbol F and the arrow representing the force. And of course the unit of thrust will be the Newton, which is the SI unit of force. So let's consider thrust on partially and fully immersed surfaces. The total thrust on a plane surface immersed in a fluid is due to the force on the surface from the fluid pressure. Consider the plane vertical rectangular surface shown partially submerged in figure 1a below. Here's figure 1a. Noting the free surface of liquid is at 0, 0. Here's 0, 0. So here's the rectangular surface. It's inserted into the fluid and it's partially submerged in the fluid. The pressure, P, on the wetted surface due to the weight of the liquid increases uniformly from 0 at the free surface to a maximum value of rho GH at the lowest edge of the surface in the fluid. So we have 0 gauge pressure at the surface and the maximum pressure at the base of the plate in the fluid is rho GH. Note the linear relationship as the pressure increases from the surface to the base of the fluid. Just notice this is the height dimension h in the rho GH formula. Thrust on our partially and fully immersed surfaces continued. So since the pressure versus depth graph shown in figure 1b here is a linear line, the average pressure, PAV, on one side of the wetted surface is 1/2 the maximum pressure. If we have 0 gauge pressure here at the surface and we have maximum pressure, rho GH, at the base, the lowest point in the fluid, then it seems reasonable to calculate the average pressure as Pmax divided by 2. So the average pressure occurs here at the centre of area. Notice that the depth of the fluid is labelled as height h here, and halfway down this height is labelled as HA, the location of the centre of area. Thrust on partially and fully immersed surfaces continued. Thus the total thrust, capital F, on a wetted area, capital A, is therefore force F is equal to P, the pressure, multiplied by A, the area. Note that the pressure P is calculated from the formula rho GH. That will have the unit of the Newton per metre squared. And A is the wetted area, and that will be in metres squared. So when we calculate our force, F, it's going to be rho times G. That's the mass density times the gravitational acceleration of 9.81 metres per second squared, multiplied by HA, multiplied by the wetted area. Note that force or thrust has the unit of the Newton, where of course HA is the vertical depth of the centre of area, C of A, of the wetted surface below the free surface in metres. That was shown in figure 1b. Here's figure 1b showing HA. This result can be shown to be true for any vertical plane surface. If the surface is subject to fluid pressure on both sides, the resultant thrust is the difference between the two total thrusts. We will consider an illustration of this later in the presentation. Let's consider example 1. The retaining wall at one end of a swimming pool is 5 meters in width, shown here on a diagram. That's the dimension out of the page. The depth of water at this end is 1,800 millimeters. We've got to calculate the total horizontal thrust on the swimming pool wall. We have to assume that the mass density of the water is 1 ton per meter cubed. So as always, the first thing to do is extract the information from the question. So I've labelled the width of the pool as capital B, and that's 5 meters. That's a dimension out of page. The depth of the pool, capital D, is 1.8 meters, shown here. So the depth to the centre of area, HA, is simply D divided by 2. In this case, that's 1.8 divided by 2. So HA is 0.9 meters. The density of the water, symbol rho, is 1 ton per meter cubed. So rho is 1,000 kilograms per meter cubed, as 1,000 kilograms in 1 ton. And the wetted area of the retaining wall, capital A, is B times D, so that's 9 meters squared. So we've got to calculate the horizontal force, capital F, so that's mass density times G times HA times the wetted area A. Inserting the values, the force is 79,461 Newton. Here's exercise 1A. A vertical side of an oil tank is 3.6 meters wide. That's a dimension out of the page. The depth of oil in the tank is 2.4 meters. We're asked to calculate the total horizontal thrust on the side of the tank due to the weight of the oil in the tank. Density of the oil is 0.75 tons per meter cubed. I'd encourage you to stop the presentation and attempt exercise 1A. The solution is very similar to that of example 1. Full work solution is shown on the following slide. So here's exercise 1A, full work solution. I'll let you review the solution at your own pace. As I say, it's very similar to that of example 1. The force from the fluid is stated here. Exercise 2A. A vertical dam wall is 40 meters wide and the top of the wall is 24 meters above the floor of the dam. If the water level is 4 meters below the top of the wall, we've got to calculate the total thrust on the wall, total force on the wall, and also what is the thrust when the water just spills over the top of the dam. As a suggestion, we should actually sketch the dam wall in the two scenarios here. The first where the water is 4 meters below the top of the dam, and the second where the water is to the top of the dam. If you think you can attempt this question without further assistance, I'd encourage you to stop the presentation and do so, but I'll show you the full work solution on the following slide. Exercise 2 is the commencement of the solution. As always, we extract the information from the question. We know the dam wall is 40 meters wide, that's out of the page so to speak, and the top of the wall is 24 meters above the floor of the dam. So I'm showing that here, 24 meters above the floor of the dam. So there's two parts to the question. First one is when the water level is 4 meters below the top of the wall, we've got to calculate the total thrust on the wall. That means it will have a height of 20 meters, the 24 total height of the dam minus 4 meters, 20 meters. So that's essentially part A of the problem. And what is essentially part B asks us to determine the thrust when the water is just spilling over the top of the dam. So here's part B, where the water is at the height of the dam. Exercise 2A, solution continued. This is part A. So from the question, the width of the dam labelled B is 40 metres, dimension out of the page. The mass density assumed to be 1,000 kilograms per metre cubed. So we're not actually given the specific density of the question, so this is assumed value. Then part A, we have to consider the thrust on the wall when the water is 4 metres below the top of the dam. So the height of the water D is 24 metres, that's the total height of the dam, minus 4 metres. So 20 metres is the height of the water in the dam. The centre of area, HA, is D divided by 2, so that's 20 divided by 2 here, so that's 10 metres. The wetted area A is dimension B times dimension D. It's the value of 800 metres squared. So to calculate the horizontal force or thrust from the water on the dam, that's rho G 1000 times 9.81 multiplied by HA 10 metres multiplied by the wetted area 800 metres squared. So the force on the dam is given is 78.48 meganewtons. For exercise 2A, solution continued. We know the width of the dam is 40 metres, 40 metre width. The density is 1,000 kilograms per metre cube. We assume that for water. Not told in the question the density of water, we always assume fresh water. And then in part A, we calculate the thrust on the wall when the height of the water, D, is 20 metres. So HA in this case, the height to the centre of area is going to be 10 metres, half the depth there. As already determined, the height of the water D 20 metres. So the wetted area A is B times D, so 800 metres squared. And our horizontal force or thrust from the water is our rho G multiplied by HA multiplied by the wetted area A. So our total force applied is 78.48 meganewtons. Here's exercise 2A, solution continued. This is now part B, calculating the maximum thrust on the wall. Here the depth of the water is 24 metres. I'll let you review the solution at your own pace. It's an identical process to that of the previous solution. What you should find is the force or thrust in this case on the wall is 113 meganewtons. Let's consider moments introduced by thrust on partially and fully immersed surfaces. The total thrust does not actually act at the centre of area of the wetted surface, but at a point known as the centre of pressure, the C of P. The centre of pressure is located at the centroid of the pressure versus depth diagram, as shown in figure 2 in here, or an immersed surface. So in figure 2, the pressure versus depth diagram is a triangle, and the centroid of this diagram is at a height x equals to a third of h above the base. So here's our linear varying pressure distribution due to self-weight of the fluid, zero gauge pressure at the surface, maximum pressure at the base. And here's our triangular shape, and the centroid location of the triangle, so there's x here, is a third of the height of the triangle, height h in this case. So the centroid is in this location here. We've reviewed centroids in a separate presentation. Thus the thrust in this case acts normal to the plane surface at a height of 1/3 of h above its base. Let's consider example 2. Fresh water is retained in a 3.2 metre wide rectangular section channel by a sluice gate 5 metres high that can pivot about its base, as shown in the sketch. When it states width of 3.2 metres, that's effectively out of the page. The height here is 5 metres, the height of the sluice gate, and the sluice gate has a hinge at its base about which the gate can pivot. This allows the water to flow past the sluice gate, but then become trapped again by the sluice gate. We're asked to determine the tension, labelled as capital T in this diagram here, in the horizontal retaining cable that's attached to the top of the gate, so it's attached up here, when the depth of the water in the channel is 4.6 meters. So this depth of water here in this channel is 4.6 meters, and the cable is attached to the top of the sluice gate here. On the following slides I'll outline the solution to example 2 and how we determine the tension or the force in the cable horizontally attached to the top of the sluice gate. So here's example 2, the commencement of the solution. So as always, we firstly extract information from the question. So the width of the sluice gate, I've labelled that as B, 3.2 meters, stating the question here. I said that's the dimension out of the page. The depth of water on the right hand side, here labelled that as D, is 4.6 meters, stated in the question here. The depth to the centre of area will be half of the depth of the water, so HA in this case is 2.3 meters. And next we have to calculate the distance of the centre of pressure from the base. That's labelled symbol X in our previous diagrams. Just shown a slightly enlarged diagram here, tries to illustrate the linear pressure distribution from the free surface to the base of the channel here. This essentially now forms a triangular pressure distribution, and we know the centroid of the triangle is a third of the height of the triangle from the base. In other words, it's a third of the depth of the water in this case, so D divided by 3, which is 1.534 meters. That's rounded to 4 significant figures here. The height of the cable from the base, labelled that as H cable here, is 5 meters because it's attached to the top of the sluice gate, and the sluice gate in the question is 5 meters high. It states in the question that the channel contains fresh water, so we assume the fresh water density, symbol rho, to be 1,000 kilograms per meter cubed. So we extracted the information here from the question. Example 2, solution continued. The first thing we need to do is to calculate the thrust on the plate from the right hand side. This is from the fresh water stored behind the sluice gate. So the wetted area A will be the width B multiplied by the depth D. So our wetted area here is 14.72 meters squared, 4 significant figures here. And then we calculate the horizontal force or thrust, which is rho G multiplied by HA multiplied by the wetted area. So the horizontal force is 332,127 newtons. Now to determine the tension in the cable, step 2 here, we need to calculate the net moment about the base of the sluice gate. So we're using the principle of moments, clockwise moments is equal to anti-clockwise moments. Let's now consider moments or take moments about the pivot. Pivot is the base of the sluice gate. Here's our principle of moments equation. Clockwise moments equal to anti-clockwise moments. Let's initially consider the clockwise moments about the pivot. There's only one clockwise moment, and it's generated by the tension in the cable, labelled T in the original diagram. For calculation purposes, I often refer to that as F cable, force in the cable. So the moment generated is the force multiplied by the perpendicular distance about our pivot point, and that's 5 meters. That's the height of the sluice gate, because the cable is connected at the top of the sluice gate. So F cable times 5 generates a clockwise moment about the pivot point. If we now consider the anti-clockwise moments about the pivot point, there's only one in this case, that will be the force generated by the pressure in the fluid multiplied by the x dimension, the height to the centroid of our pressure distribution in the base, the channel, and that will essentially generate an anti-clockwise moment about the pivot. So here's the calculations. F cable multiplied by the height of the cable from the pivot point, 5 meters, is equal to the force from the fluid multiplied by x, which is the distance to the centroid from the pivot. Simply rearranging now for force in the cable, that's Fx, divided by the height of the cable. Inserting the values, the force in the cable is equal to approximately 101.9 kilonewtons. And that's equal to T, the symbol used in the question for the tension in the cable. That concludes the solution to the example. Let's consider exercise 1b. Now, seawater is retained in a 6 metre wide rectangular section channel by a sluice gate that can pivot about its base, as shown in our sketch on the right hand side here. We've got to determine the tension in the horizontal retaining cable attached to the top of the gate when the depth of the water in the channel is 5.25 metres. The density of the seawater is given as 1020 kilograms per metre cubed. Here's the answer for the tension in the cable. Slightly different configuration as from example 2, in that the water is now on the left hand side of the sluice gate, not the right, but exactly the same process is required when generating the solution for exercise 1b as for example 2. I'd encourage you to stop the presentation and use your solution to example 2 to help you solve exercise 1b. I will briefly outline the full work solution on the following slides. So exercise 1b, here's the commencement of the solution. I'll let you review this at your own pace. Example 1b, solution continued. So here's part 1, calculating the thrust on the plate, this time from water contained on the left hand side of the sluice gate, but the approach is exactly the same. We calculate the force generated by the pressure in the water. And part 2 here, calculate the net moment about the basis of our clockwise, anti-clockwise moment. Again, I've referred to the tension in the cable as F cable here, but the approach is exactly the same. We can rearrange the equation to find the force in the cable. Here's exercise 2b. I'm going to let you review this at your own pace, so you can read the question at your leisure. I will very briefly outline the full work solutions to exercise 2b on the following slides. Here's exercise 2b solution, and I'll let you review this at your own pace. Exercise 2b, solution continued. Part 1, generating the thrust on the plate from the left hand side, the water contained left hand side of the sluice gate in this case. Force calculated here. And step 2 here, calculate the net moment about the base, trying to find the force in the cable. Label this T on this diagram, tension in the cable, and that's calculated here. I will leave you with question 1b to attempt at your own pace. No solution is provided, but the answer is given here in the square bracket. And question 2b, again no solution provided, but the answer is shown here in the square bracket. Just be careful in this question, as specific weight of oil is stated, 8.34 kilonewtons per meter cubed. And again, if you have reviewed the previous presentations, you will understand specific weight is actually weight density, and hopefully you can use that appropriately within the question. Weight density is essentially mass density multiplied by gravitational acceleration. Exercise 3b, which is a slight variation on the solution sequence. In the previous question, we've only had fluid on the left-hand side or the right-hand side of the sluice gate. With exercise 3b, we have fluid on both sides. So I'm going to outline exercise 3b to you. A vertical plate is used to separate two areas of a large industrial rectangular fuel tank, 6 meters high and 6 meters wide. On the left-hand side of the separator plate, the fuel is 4.5 meters high, and on the right-hand side, the fuel is 1.5 meters high. Taking the density of fuel as 780 kilograms per meter cubed, got to calculate the net horizontal thrust on the separator plate and the position of the line of action from the base of the tank. Exercise 3b requires a slightly different solution, but I'll outline the solution on the following slides. So exercise 3b, here's the commencement of the solution. On this slide, I just essentially extracted some of the information from the question. So on the left-hand side, we have fluid 4.5 meters in height. On the right, we have fluid of a height of 1.5 meters from the base. To calculate the location of where the force in the fluid on the left-hand side here occurs, that's the height divided by 3. So our x dimension is 1.5 meters on the left-hand side, and on the right-hand side, dividing 1.5 by 3, the x dimension is 0.5 meters for the force from the fluid on the right-hand side of the plate. Exercise 3b, solution continued. I just extracted all the information from the question. You can let you review this at your own pace. I've included the diagram from the previous slide as well. The mass density of the fuel in this case is 780 kilograms per meter cubed, not water this time. So essentially here we are considering both sides of the plate. So we have a left hand side D value, a left hand side HA value, and a left hand side X value, and then we have a right hand side D value, right hand side HA value, and right hand side X value. So as I said, we're considering the left hand side and the right hand side information. It's all extracted from the question. Exercise 3b, solution continued. So now as before, we calculate the thrust on the plate, but this time we have a left hand side thrust to calculate, shown here, and a right hand side thrust to calculate, shown here. But exactly the same approach is required to calculate the wetted area, calculated the horizontal force, using the rho g HA formula. Part 3 here, we have to calculate the net horizontal force, called it F net here. So that's simply the force from the left hand side minus the force on the right hand side. So we can calculate the net force. There's the value of the net force, and its sense is from left to right. Step 4, we calculate the net moment about the base. So I've called that M net here. So basically we have FL times XL for the left hand side, the force times the distance to the center of the force from the base, and we minus the force on the right hand side times its distance from the base. And that allows us to calculate the net moment, and that will have a clockwise sense about the base. Finally, part 5, we've got to calculate the line of action, label it as Z here, from the base. So Z is equal to M net, calculated above, divided by F net, also calculated above. So again, inserting the values, we calculate the distance from the base of the line of action of the net force. So a slightly more complicated solution, but hopefully you can follow the steps. So exercise 3b, solution continued. Just included this diagram here to try and illustrate the previous calculation. We have the net force, shown here, is from left to right from our calculations. It's some height z above the tank base. So the force times its perpendicular distance about the tank base generates a clockwise moment, which is calculated from the formula M net. Net moment is equal to the net force multiplied by the perpendicular distance from the line of action of the force about the tank base. Rearranging, distance z is the net moment divided by the net force. So we can calculate z as shown here, distance from the base. As I'll leave you with exercise 4b to attempt at your own pace. This essentially follows the same steps as exercise 3b. That concludes the presentation, which I hope has been of some use to you, and as always, thank you for viewing.